Alrighty, so today we're going to learn one new type of series, that's the P series, and then a smaller subset of that is the harmonic series. So we'll have a P series test that we'll add to our arsenal of series, just like we had the geometric series test. And then this nth test for divergence is going to be something that works on any series, but it only lets us find if it diverges. So let's talk about this first. There's a statement out there that says if a series converges, so in this box here, if a series, this is a series, converges, then the limit as n approaches infinity is equal to 0 of an. Now that doesn't mean that this is different than the series converging completely, right? This is the limit of the sequence, right? The thing inside. So if the sequence converges to 0, right? So if the series converges, then we are guaranteed that the sequence converges. So series converging, that guarantees that the sequence generating that series converges. Which makes sense, right? If we're going to add up all these terms and that approaches a value, then it would make sense that the individual terms themselves approach value. However, the opposite is not necessarily true, okay? So if the sequence converges, or if the limit as n approaches infinity of an equals 0, that does not guarantee, so it does not guarantee that the series converges. So we'll see an example later about this of a sequence that converges and the series does not converge, but this direction is true. And so more importantly, the contrapositive of a statement that is true is always true. And so the contrapositive here is true as well. So the contrapositive is flip it and negate it. So if the limit as n approaches infinity of the sequence does not equal 0, then the series has to diverge. So this is going to be our nth term for divergence. The important part here is that this is a test for divergence. You cannot take the limit as n approaches infinity to say that the series converges, right? So this is super duper important, okay? And if the limit doesn't equal 0, what does that mean? That doesn't mean that the series converges because it's a test for divergence, not convergence. It just means that the nth term test is inconclusive, okay? So this is something you're always going to want to use first. Whenever you look at a series, you'll always try the test for divergence and see if it works. And if it doesn't work, then you'll move on. So let's look at some examples. So if we take the limit as n approaches infinity of this guy right here, these both are polynomials of power 1, so they're growing at the same rate. So if they're growing at the same rate as we go to infinity, then we'll look at the leading coefficients to find the limit, and so that'll be 1 over 1, or just 1. So this limit is equal to 1, and the nth term test for divergence says if the limit is not 0, so this limit is not 0, then the series diverges. So this guy diverges because this is not 0, this diverges by the nth term test. This series here, if we take the limit as n approaches infinity of 1 plus 3 to the n over 2n, so we're doing the limit of the sequence, right, that generates our series. These exponential functions are both growing pretty fast, but 3 to the n is going to grow much faster than 2 to the n. And so this little guy on the end is just not going to really matter. He's just adding 1. So these are going to grow. 3 to the n is going to grow much faster. And so this will go to infinity because the top will be growing much faster than the bottom. And is infinity 0? No. And so if the limit is not equal to 0, which this is not 0, then the series diverges. Here, if we take the limit as n approaches infinity of 1 over n. The bottom growing to infinity, top staying at 1, will go to 0. So should we say that it converges? No. If the limit is equal to 0, then it's just inconclusive. You can't say anything else. So here, if the limit is not 0, you get to say it diverges. If it's 0, you can't say anything at all. It might converge, it might diverge. So you would have to use another test. So this is inconclusive, and we'll have to use another test. But at this point, we don't have any other tools for this guy, so we'll wait. It might converge, it might diverge. This guy down here is a factorial. You'll see these a lot in this part of the world with sequences and series. They don't really play nicely, but one thing that we know about functions, growth rates, this is kind of helpful, is that the slowest growing function is any logarithm. So a logarithm is the slowest growing function. And then stuff that grows a little bit faster than that are polynomials. And we obviously know the degree of the polynomial will make it grow faster, right? So a third degree will be growing faster than a second degree polynomial. And then after that, after polynomials, exponentials are the faster growing function. We've talked about this before. But then the fastest growing function of it all is a factorial. So n factorial is the fastest growing function of all. So if we go to take the limit here, as n approaches infinity of n cubed over n factorial, we have a polynomial of degree 3 on the top and a factorial on the bottom. So the bottom is going to grow much faster. So if the bottom is growing faster than the top, then this fraction will go to 0. And so again, this is inconclusive. We can't use the nth test for divergence. So it's really easy to use to start, right? You find a series, take the limit as n approaches infinity. If it doesn't equal 0, you're done. You get to say it diverges. If it does equal 0, then you're going to have to use another test, and you'll have to move on to another option. Right now, we won't touch this D example for a while. We'll touch this example today. Okay, so another series that we're going to learn about today is the P series. The P series is very nice. It's similar to the geometric series, but just a little bit different. And so a P series is something of this form right here, where you have n in the denominator now, and P is in a power, right? So that's your number, and P just has to be positive, okay? So let's look at a couple examples of P series here. So this first example here, if you remember, n has to be in the denominator. So let's write this as a positive exponent. And we'll have 1 over k to the 0.8. And so this has the P series form. So here, this is your P in the power, and k is in the denominator. So as long as it's k to a power, and as long as P is positive, so 0.8 is positive, then this is a P series. So this is a P series with P equal to 0.8. Here, if we rewrite this one as 1 over 2 to the n, this is not a P series because the power needs to be the number, right? Here, n is in the power, so this is geometric. So when n is in the power, this is geometric, right? So this is not a P series. So the number has to be in the power and the n has to be in the bottom to be a P series. This guy here, if we rewrite this, will be 1 over k to the 4. So the variable, or the n or the k, is in the bottom. The p, the number, is in the power. So this is, with p equal to 4. This guy here, if we move the n to the bottom, it will be 1 over n to the negative 2. So this is not a P series. Because remember, p has to be positive. So that's why it's important that n is in the bottom, right? So if n is in the top with a power number, that's not a P series. And then here we've got k in the bottom with a power of 1, a little invisible power of 1. So we do have a number in the power and k is in the bottom, and this is a P series. with p equals 1. Specifically, this is called the harmonic series, and we'll talk about it in a minute. Okay, so once you know that something is a p-series, it's really, really easy to see if it converges or diverges. The only thing you have to be careful of is it's very similar to a geometric series. Okay, so a p-series converges. All you have to do is know what p is. If you know what p is, then if p is greater than 1, then we converge. If p is between 0 and 1 or equal to 1, then we diverge. And remember, p has to be positive, right? So there's no, if p is negative, then it's not a p-series, right? So p less than 0, not a p-series. So that would not work. Okay, so we are going to look at these examples here to see if they converge or diverge here. So we will look at this guy first. Let's go ahead and write this as 1 over k to the 3 over 4. And if we write that like that, then it's pretty clear to see that p is equal to 3 over 4, which that is less than 1. So since that is less than 1, then it diverges. So we've got the opposite going on here from the geometric series test. This next problem here looks like it might not be a p-series because of the -1, and you should be careful of that. If there's other stuff in there and it's just not the n to the second power, then you should be careful. But if you look at what's happening here, n-1 just means that the number down there will be 1 less than the previous term. So if we plug it, so the first one starts at 4, so the first term will be 1 over 4 minus 1, which is 3 squared. The next term will be 5, plug in 5, so you'll have 1 over 5 minus 1, which is 4 squared. And then you'll have 1 over 5 squared, and then 1 over 6 squared. So this is still a p-series because the p in the power is staying the same, right? You could even re-index this if you wanted to start at n, right? If you said n started at 3 and went to infinity from 1 over n squared, then that would be the exact same thing as this one right here, because you would start at 3 and then 4 and then 5 and then 6. So if you have an n-1 here, you can always re-index by just subtracting 1 here and starting. So this is still a p-series with p equal to 2, okay? And so this diverges. No, this one converges, sorry. So p is greater than 1. So if p is greater than 1, then it converges. And so the p-series is the opposite of the geometric series, right? So if p is greater than 1, then it converges. If p is less than 1, then it diverges. Geometric is the opposite. They both diverge at 1, but how big it is changes. And I'll show you an example here in a second why that might help, why it's that way, to help make sense of that. So this last example here is actually not a p-series at all, because the k is in the power, not the number. E is the number here. So if this was 1 over k to the e, then that would be a p-series. But this is not a p-series here. Not a p-series. Because the k is in the power. When the k is in the power, this is geometric. So let's go ahead and still use the geometric series test to see if it converges or diverges. So if we rewrite this as 1 over e to the k, now we can have the k in the power and the number inside. So now that's our ratio. R is 1 over e. And if you remember, geometric series converges when the absolute value of r is less than 1. And e is 2.7, so this number will be less than 1. So this guy converges by the geometric series test. Okay, so it does converge, but it's not a p-series. Because remember, the p has to be the number and the power. Okay? So one more example here. We have a series, and we need to figure out this is a p-series. It tells us that, but why? So we need to kind of write the general formula for this. So you can definitely see that we have a 1 in the top for every term, and each term has a cube root. So we definitely know this is being raised to the 1/3 power. And these numbers inside are all perfect squares, right? So this is 2 squared and 3 squared and 4 squared and 5 squared. So that's your n, right? It's going up by 1, so this one we could say is 1 squared cube root, because that will just be 1 in the bottom. So then we've got an n squared that's being raised to the 1/3. So this is 1 over n to the 2/3. So this is a p-series with p equal to 2/3. And so this diverges because p is less than 1. And our very last example here is this harmonic series I have been telling you about, okay? So the harmonic series is technically a p-series with p equal to 1. So it's just a p-series of p equal to 1. So if p is equal to 1, we know our p-series test says that it diverges. But it's special series because we see it all the time, so we have a special name for it. But it does diverge because it's a p-series with p equal to 1. Okay, so the harmonic series diverges. Okay, but one thing to note about this, just a kind of fun fact, is remember how I told you, so our sequence, 1 over n, that sequence, so the list of numbers, this sequence itself converges, right? The limit as n approaches infinity of an, when that's the harmonic series, this equals 0. So the sequence converges, right? But the series diverges by the p-series test, okay? So although the terms get closer and closer to 0, they don't get close enough to 0 fast enough for the series to converge. So this is why if the limit does equal 0 of the sequence, that's why the nth term test for divergence is inconclusive when the limit equals 0, because sometimes when the limit equals 0, the series will converge and sometimes it will diverge. And here's an example of diverging. I also have a little explanation for, since the geometric series and the p-series are so similar, like greater than 1, less than 1, but kind of opposites, if you want to stick around for the rest of the video, I have a little sidebar for why those work the way that they do, and a good way to think about it. But if you want to be done here, you're welcome to, but if you find that would be helpful, feel free to stick around.